anion test. If you have an unknown powder and you need to start with a series of tests to determine what is in it, the first one is to remove the carbonate because it could complicate some of the other reactions. Okay, so you would first take out the carbonate by adding acid. They say this should be done because the anion will give a positive result in all of the other tests. Okay, so when you do a test, you add a little bit of acid to it because the acid is going to remove the carbonate. No. Okay, then they say to identify the other anions, a precipitate of an insoluble salt of the anion is made. The insoluble sulfate is barium sulfate, and we do this by adding barium chloride or barium nitrate. No. And then the insoluble chloride is silver chloride. We do this by adding silver nitrate. Are you with me? Okay, but very important when we start with these tests, then you first remove the carbonate because it interferes with the test forming the precipitate, and you will think it's maybe the hydroxide, which it isn't. All right, that's the one thing. Then I want you to turn back to page 50 in your textbooks. And this has got to do with the test, for example, with copper. We take copper ions in solution and we add, for example, sodium hydroxide to it. What will we get? Copper hydroxide, then this stuff is blue. All right? We do the second test for copper ions with ammonium hydroxide, and with a few drops, we will get the copper hydroxide precipitate, which is blue. But if I go and add excess ammonium hydroxide, when we did the cation tests, we said, what do we get? A deep, dark blue solution. Now this dark blue is due to the ammoniated complex ion. All right. Now, okay, I've got them summarized here. I'll read the bit. Okay. It's the ammoniated complex ion. This dark blue solution is due to the okay. Now we don't go into much detail in terms of complex ions. It sort of becomes a branch of chemistry that involves quite a bit of stuff. But we do just very basically do, for example, the complex ion involved with the test for copper. All right. Now, the copper hydroxide. Let's go here. Starting off, yes. If I have white copper sulfate and I add water to it, we get the hydrated copper ion. Okay? In other words, it's going to look like this. It's still the copper ion, the 2+ ion, but it's hydrated. So this would be, for example, blue copper sulfate in solution. All right. When we add sodium hydroxide or ammonium hydroxide to it, let's take the ammonium hydroxide, we get the insoluble copper hydroxide that is formed, and this stuff is blue. Okay? When I add excess ammonium hydroxide, I get the ammoniated complex ion, and this is the copper 2+ ion, but it now bonds onto the ammonium ion. There's 4 of them, and we have the +2 ion. All right. This is in your textbook. They actually put this whole thing in a bracket because the charge is applicable on the whole thing. Similarly over there. So if you go in your textbooks on page 50, I'm going to read on the left-hand side. They say in this activity there are 3 changes. Firstly, the addition of water to white anhydrous copper sulfate caused it to change color to blue. All right? Now this blue liquid that we had was the hydrated copper iron. The formula for the hydrated copper iron is that one. That's the hydrated copper complex. You must know that. Then, the test for the copper 2+, the next step in your books, they say, then a light blue precipitate was formed. But what did we do? We added a base, either the sodium hydroxide or the ammonium hydroxide. The blue precipitate that we got was this one. That is a solid. Whether it was with sodium hydroxide or whether it was with ammonium hydroxide, this was just a normal insoluble salt. Then if you go one step further with the ammonium hydroxide, when we add excess ammonium, it's as if the ammonia displaces the hydroxide. And that is why we get a soluble ammoniated complex iron. Okay? Yeah, it doesn't matter. It's in water. It's in water. So it forms ammonium hydroxide. Okay, so then just next one down, they say in the white anhydrous copper sulfate, the copper ion has no color. But when water is added, a complex ion is formed. The ligands are water molecules. What is a ligand? It's a covalent bond that is formed where one part gives both the shared electrons. Now remember, the water molecule over here, we have 2 lone pairs. So water can be the ligand. Over here, the ammonia is the ligand because ammonia, yes, has got a lone pair to form the complex ion by means of a coordinate bond. Are you following me? All right. I'll read further. They say the ligands are water molecules. In this case, 4 water molecules will share 1 lone pair each with a copper 2+ ion. Then this is shown in the equation, and they give the formula for the complex ion. And then in the next paragraph, when the ammonium hydroxide, the ammonia solution, all right. Remember I said to you, ammonia plus water forms ammonium hydroxide. All right. That is why sometimes they write it like that and sometimes they write it like that because we're in watery solutions. Okay.
Why do they, does the order of which you write hydrogen?
Yes. Because the positive ion is normally written first.
So that's, what about the covalent?
Carbon is usually written first. Sulfur is usually written first. That you will sort of, yeah. You know, in grade 8, I won't necessarily penalize you if you did OHNH4. But when we get to grade 10, 11, you need to get them right.
Hydrogen oxide. Why couldn't you write it OH2?
No, because water is written H2O. Hydrogen is the positive ion. Oxygen is the negative ion. It's covalent, I know. But hydrogen forms, it acts like a metal. Do you understand? Okay. There are rules in general. A lot of it is experience. Okay. Yeah, they will penalize you. Yes. There will be rules for the order. When we do organic chemistry, you'll see as well specific way of writing the compounds. Okay. I want to carry on. So when the ammoniated hydroxide is added, the ammonium hydroxide is added, the first reaction that occurs is the formation of insoluble copper hydroxide. That was this one. Over there. That one. And then when excess is added on the right-hand side, just this first second paragraph. When more ammonium solution is added, a new complex ion forms in which the water molecules are replaced by the ammonia molecules. The new complex is formed, it's darker blue. I'm sorry, I made a mistake over here. It's NH3. Okay. 4. So it's the ammoniated complex that forms. Then they just say in the next section, transition metal complex ions are common and some are very important to us. One example is the molecule formed when the protein molecule hemin joins the transition metal ion. Then we get hemoglobin. Yeah. Okay, this molecule is called hemoglobin and has the property of being able to form a complex when the ion shares a lone pair of electrons on an oxygen molecule to carry the oxygen. Okay. That then. Please reference this last section with a test for copper back to page 50, because it sort of actually fits in with the test for the copper. And they do it completely in a different place in your book. Okay. So take note, it's on page 50. All right. Now, at this point, I'm basically finished with the test for the different metals and non-metals and gases. We have to carry on. The next section has got to do a little bit with industrial processes. Now, the industrial processes, you need to know a little bit about them. They do ask now and again. So it's a little bit of just root learning work, which I know you love. Yeah. All right. I'm just going to go through the theory as it is in the textbook, starting off the industrial processes based on lime. Now, lime, if you heat calcium carbonate, all right, you heat it up, it decomposes, and it forms calcium oxide plus carbon dioxide. If you take calcium oxide and you add it to water, we get calcium hydroxide. All right? This one is known as limestone. This one, quicklime, or just simply lime. And this one, slake lime. Lime water is calcium hydroxide shaken up in water. It's not very soluble, it's very slightly soluble, so you shake it up over a period of time. Yeah, and then you filter off the excess undissolved copper, calcium oxide, and that forms lime water. Okay, it's lime in water. All right, you need to know this. If you don't know it, it's very confusing. So they say there by the industrial processes, lime has been a very basic, important basic substance with many uses. Lime, however, is used in common English to refer to a number of different compounds such as quicklime, slaked lime, and limestone. You must know the difference. Then limestone or rock is calcium carbonate. It occurs widely throughout the world. Was formed many millions of years ago. I don't agree with the millions of years ago. When shellfish and other sea creatures died and their remains fell to the bottom of the sea, whatever, how they were formed, doesn't matter. Then the shells are made of calcium carbonate. And then over the years, these shells became compressed into layers. There's a whole part on geography where they talk about all these funny types of rocks that are formed and metamorphic. And no, you don't need to know that. Just know the difference between those three. Then marble and chalk are also forms of calcium carbonate. Marble is produced when limestone has been subjected to high temperatures and pressures in the Earth's crust, which caused it to melt and then solidify again. We call this rock metamorphic rock. You don't have to know that. Some very fine quality marble is found in the hills around Karabip. Limestone is widely quarried. What is a quarry? It's a hole dug in the ground from which we pull out rocks. No, we quarry gravel for building, making concrete, building roads, etc. Its main use is as a building material. In the olden days, in Europe, the cathedrals, etc., were built from limestone, basically marble rock. It's not always the pure metamorphic rock, but it is limestone. And that's one of the big problems in Europe is due to the acid pollution. These structures are starting to crumble. So they've got processes, they clean it up and they put a layer over them that protects it. Yeah. Yeah, I don't know if they'll cement over it, but they to try and preserve the natural structure as it was built 500 years ago, type of thing. Especially the cathedrals, it was a lot of actually specialized stonemasonry to build those things. Okay, so limestone then is widely used. And why can it be used very widely? It is easy to cut into regular shapes, okay, which makes it particularly good building structures. It's not all that, you can chip it off. Do you understand? And once you've put it into place, it's very strong under compressional forces. So it's good to use. It's a yes. Okay. They say the main use nowadays for limestone is to make cement. All right, now it's heated with clay. How do we make cement? Limestone, calcium carbonate is heated with clay. Clay consists of calcium and aluminium silicate. All right, it's heated together. Where are we now? Okay, it's heated with clay in a furnace at about 1,400 degrees Celsius. All right, it is a product of a mixture of calcium and aluminium silicates. These are in powder form when they come out of the furnace. When water is added to the mixture, the two silicates form crystals. If I take cement and I put some powdered cement, the stuff you buy in bags, I put it in my hand and I drop some water into it, it becomes hot. Why? When I've heated this up at 1,400 degrees, why do I heat it up that high? I'm trying to heat off the water of crystallization. When you add water back to it, if I put in energy to get rid of it, if I put water in, it's going to give off energy. All right. So it becomes warm. In concrete, it's the calcium and the aluminium silicate that forms long interlocking crystals if you allow concrete to dry out slowly. In our country, when you've built a new structure, you stand and you keep the concrete wet, especially in the winter. Why? Yes, because if you don't do it, the concrete will be very weak. It will crumble. Why is that? If you could look at it microscopically, you will see in concrete that has set very hard, that has been allowed to dry out slowly, it has long interlocking crystals. In concrete that dries out very rapidly, these crystals can't grow, and they are shorter and smaller, and they don't interlock as well, and the concrete becomes crumbly and weak. Okay. When water is added to the mixture of the two silicates, they form long crystals which lock around each other as they grow. If sand is added, the particles of sand are also locked into the crystal and the whole mass is very strong. We refer to this as concrete. Concrete consists of sand, cement, and water. We can add gravel to it. We can add steel bars to it. All right? Reinforced concrete. Or steel mesh in it. It's to make it stronger. But cement, the stuff you buy in the bag, is made from calcium carbonate and clay that has been heated together to a very high temperature. Okay. They say when concrete sets, it does not dry out. The water in it becomes part of the silicate crystals which are formed. In other words, if there isn't water, these crystals can't form and your concrete is weak. We refer to the water that is part of the crystal as water of crystallization. You remember when we did the stoichiometry calculations? There was one where we calculated the percentage water of crystallization. All right, it's the same thing that they refer to. We refer to the water that is part of the crystal as water of crystallization. The slower... Okay. The slower the crystals are allowed to form, the bigger and stronger they are. This is why it's important to keep the concrete wet for a week at least, as it sets. Now, particularly in warm climates, particularly in dry climates. Warm, wet climates aren't a problem. But dry climates, here as in the winter, it is a problem. Yeah. Ja, dit is hoekom hulle, as hulle dit gemaak het deesdae, dan hulle hier 'n masjiene wat dit in plastic wrap en dan spuit hulle nat en hulle vou hulle toe dat die water nie kan verdamp nie. Dan kan die baksteen groei. Dan word hy sterk. Ja, as om te keer, om die verdamping te keer, want dit is buitengewoon erg hier by ons in die winter. In die somer ook baie, want dit is warm, maar in die somer is dit beter want daar's meer vog in die lug. En die konkreet kan die vog uit die lug uit ook absorbeer. Maar by ons in die winter is dit fataal om 'n struktuur te bou en nie nat te maak nie. Okay, alright. Then another use for limestone is a flux in furnaces for extracting metals. And when we do the extraction of metals, we will have a look at the use of limestone as a flux. Quicklime and slaked lime. Two kinds of lime are calcium oxide and calcium hydroxide. They both are made from limestone. This is a very large chemical industry. To make quicklime, the limestone is heated to over 1,000 degrees. As it decomposes, it forms carbon dioxide and calcium oxide, which is quicklime. There is the equation on page 90. Please take note. It can be asked of you to write them. I've done them. Did I do them over here? Yeah. All right. And you must know them. Then calcium oxide and quicklime does not have many uses because it reacts with water so easily that it can react with moisture in the air. It's actually very difficult to fill a bag of calcium hydroxide and leave it standing around in Namibia in the summer because there's lots of water vapor in the air. Okay. This means that it is difficult to store. It must be kept in sealed bags or bottles. Once these have been opened, the quicklime soon reacts to give slaked lime. All right. It has a rather unpleasant property that it reacts rapidly with living or dead animal matter and must therefore be handled with great care. You mustn't breathe it in, for example. Because of this property, it is used to destroy diseased animal carcasses, such as cattle, etc., that have been slaughtered because they are diseased. I can remember, this is about 20 years ago, maybe even longer. Daar was varkpes onder die varke hier rond. En toe het die ouens gate gegrawe en die varke daar ingegooi en quicklime oorgegooi, né? Covered them up and because it extracts all the water from it. No bacteria can rot and grow further. It's to stop the diseased carcasses, the diseases from spreading. Then, three main uses of calcium hydroxide are as a fertilizer. Why would we use it as a fertilizer? The plants don't need to take it up. Is it acidic or basic? It's a base, a metal hydroxide. So when soil becomes too acidic, we can add this to the soil. It lies in the soil, it's inert, but when it rains and it becomes wet and there's an acidic medium, it will react and neutralize the acid. Okay. A fertilizer, it's used for making sodium hydroxide from salt in the alkali industry and for neutralizing acidic industrial waste. And then there's a flow chart of the limestone industry. There's a part on the alkali industry. They refer to the Solvay process. Now, the Solvay process, people, in your syllabus, they specifically refer to the Solvay process. They have never asked it in all the years to describe it from beginning to end. At best, they ask 1 or 2 marks on it. It's a section of work that I personally don't like, because the Solvay process differs slightly from one place to another. Okay? So during the Solvay process, if you look on page 91 on the right-hand side, it uses calcium carbonate and sodium chloride to make sodium carbonate and calcium chloride. All right, so ions are swapped around. Unfortunately, this reaction does not happen easily, and it is done in several steps. Step 1, calcium carbonate is heated. You have to go and learn this. There's no way beyond it except learning it out of your head. But if it's really hard for you to go and learn this, because even if I had to go and sit and write it down, I'll make mistakes. I don't work with it often enough, no. Okay, and they have really never ever asked anything much on the Solvay process. So if you reckon it's worth a chance and you don't bother with it, then you don't. But just know it is part of the syllabus. Okay. So step 1, calcium carbonate is decomposed into calcium oxide and carbon dioxide. Step 2, ammonia and carbon dioxide are bubbled through the salt, giving sodium hydrogen carbonate, which is not very soluble, and it crystallizes. Step 3, the ammonia is recovered for reuse. Step 4, sodium hydrogen carbonate is heated to give sodium carbonate. They recover the carbon dioxide for reuse. All right. And then there's a flow chart, all the different uses of these substances. You need to know one or two of the uses. Okay. Then, sulfuric acid industry. Now, there are 2 other industrial processes except for the Solvay process. We talk about the contact process, and the other one is the harbor process. The harbor process we did in grade 10, somewhere. Okay, we will redo the harbor process. The contact process is the process that they use to make sulfuric acid with. Sulfuric acid starts out with sulfur that is burnt to form sulfur dioxide. All right? The sulfur dioxide is oxidized further to form sulfur trioxide. And if we add sulfur trioxide to water, we will get sulfuric acid, although it's never just as simple as that. Okay? There are some particular problems that we experience with this reaction, and I'm going to just go through that book as it is written there. So on page 92, we will start with just start at the top. Manufacture of sulfuric acid, one of the biggest world chemical industries. All right, sulfuric acid is a chemical from which many other useful materials are made.